So, Unit 0, Introduction to Physics. Chapter 1. Now, the chapters do relate to the physics book that we use. The physics book that we use for this class is Paul Hewitt's Conceptual Physics. It is probably the best conceptual physics book out there, and there are probably very few people who would argue with that. And Mr. Hewitt does a wonderful job of explaining the concepts with very little math. Okay? And I use some of his tools as a teacher within this class. I even use it in some of my other classes because it's good stuff. So we do have a book. We just don't really use it much besides to prop up our ramps when we get into the lab. Because if I told you to go and read a chapter out of your book, one or two of you would maybe do it. The majority of you would go, yeah, that's not happening. Okay? But it's there if you're like, what chapter are we covering? And so that's there. That's why it has that chapter 1. And I like to use cartoons as when we can, because I think satire helps. And so we define science, and whether it's chemistry, physics, geology, biology, as a methodical exploration, kind of cut off there, of nature. Now you would think, but physics isn't nature. Physics is all about nature. It's just the motion and moving inside nature, followed by a logical explanation of that observation, what you see. Okay? And I like The Far Side. It's a little bit older of a comic, and we have it in these two mathematicians sat there, and it looks like they've done some really crazy, weird math that most of us will never understand, myself included. And it all equals 0. And when you read the bottom, they're like, oh, the purpose of the universe. And it equals 0. So it's satire, it's humor. It's like, oh, so what's the meaning of the universe? Well, Far Side says 0. That's what it is. But they went through the process. And that's what we really will kind of start looking at, is the process that it is. So what is our fundamental goal? We want to understand what's governing the phenomena that we see. Why does this happen? Now, physics is that sometimes easier to understand than, say, chemistry. Because chemistry deals with things that are extremely small. Our brains have a hard time understanding things that are extremely small and extremely big, or happen over extremely long periods of time. That's geology. It's just hard for us. That's why in astronomy, to shorten the amount of time or distances to a number that we can comprehend, we have light years. That's really the only reason light year as a form of measurement exists. It's so I can say, oh, it's 5 light years away. You're like, oh, I've seen 5 of something. Or in geology, they call it eons. Well, it's 4 eons ago. I've seen 4 of something. I know what that looks like. The fact that it's millions of years or billions of miles is hard for our brains to understand and comprehend. And so that's why physics, in the Newtonian physics that we cover in this class, is sometimes easier to understand. Because we're dealing a lot of times with things that we can see and things that we can measure. And that's the important thing. That we want to be able to see, we want to be able to work and do as those things happen. These concepts use the scientific method, which is a very step-by-step process. This scientific method is very also hard for some people to understand in this day and age, of where everything is instant gratification. Right? Almost instantly after posting something on Instagram, you get a like. Or somebody views your video on Snapchat or TikTok or wherever. Okay? It almost happens instantaneously. And you get the euphoric feeling of, ooh, somebody watched it. Ooh, somebody liked it. The scientific method is a long, drawn-out process. It takes time. Why does it take time? Science and the scientific method take time. Why does it take time? Because, well, once you have to observe it, and it's not just you see something and it happens. You know, you see a person slip on the street, you're like, ha, funny. Yes, it is. They must have slipped on ice. That's not science. That's just the observation. You're not going to run experiments. You might go, oh, if there's ice over there, I can bet you I could slide over there looking cooler. No, that's not an experiment. That's just having some fun. Making an observation, having that problem is what it is. Running the experiments. And you can't just run the experiments once. You have to run them multiple times before you even start to gather enough evidence to even remotely determine whether or not your hypothesis is correct. And even if you find that your hypothesis is correct, you rerun again it, but changing a variable, which we'll talk about in a little bit, to see if that changes anything from your experiment. Because that's how the process happens. It's probably almost 8-10 years ago, but a number of years ago, there was a group that said that they were able to achieve faster than the speed of light. They were able to get particles moving faster than the speed of light. Published their results. That opens up to criticism now. Okay? In the scientific community, which means and you make something that bold, you better have evidence to back it up. Other laboratories try to replicate their experiment. Other scientists go to that same laboratory and try to replicate that experiment. They're going through, check your hypothesis over and over again. Because if you're making a bold statement, we're going faster than the speed of light, that kind of changes some things in physics. Nobody was able to replicate the results. Even those that went to the same laboratory. Therefore, those scientists had to retract, which is very insulting to do as a scientist, to retract your paper and say, yeah, maybe we were wrong. Especially with something so bold. They had to go through the process. Now, everything that goes through the process does not guarantee that you become a scientific theory and or law. That's like that elementary scientific method. And after so many times it becomes a theory, and after so long it becomes a law. That's not how it works. Theories and laws are defined differently, and we'll talk about that in just a little bit. So what is a hypothesis? A lot of times they want to say just an educated guess, but it's not just an educated guess. Okay? There's an additional part to that. Explains an observation. A hypothesis is not just a guess. It is an explain why. And a hypothesis must be written in a way that it can be tested. So that you can test the variables. Test what's happening. And you might find out after you test some variables and you modify something, you're like, oh, that kind of changes it. So what do you do with your hypothesis? You change it. And then you test it again. And then you test it again. And then you test it again. And then you change some variables. And you're like, oh, that changes it too. And so you got to change some more things and change it again and change it again. That's why science takes so long. It takes a while for things to happen in science. So, an observation. A sheet of paper is dropped and falls to the ground. A hypothesis, is there attraction between the paper and the ground? The paper really likes the ground. A bad hypothesis, objects fall. Thank you, Captain Obvious. Right? No, there's got to be, it has to be testable. Think about, Newton was not the first person to have an apple fall on his head. That's a scientific fallacy. It's just a story we make up to help people understand how science sometimes works. We make up stories. Okay? He was not the first person that had an apple fall and hit him in the head going, gravity! No, that's not how it worked. He was probably sitting in an apple orchard watching things fall, and he felt kind of like they're falling at a constant rate. And he would probably notice that. And then he invents calculus to help explain why gravity and the laws of motion work. Because he needed to, couldn't use just algebra, so he had to invent calculus to help him explain mathematically what was going on. And to finish up, what we did was we experimented. We controlled the properties of the system. Now, our recorded measurements for the demonstration done was just crumpling a paper, holding a paper, folding the paper. We could fold it again and try to modify some more things, and that would be more experimentation. And our observations are really the recorded measurement. What would be a better recorded measurement if we actually measured how high it was when I let it go, so that was consistent, and also timed it, right? I could make that crumpled up piece of paper fold just as long as a uncrumpled up piece of paper. You just take it higher up, right? But see how then the variables are different. And that's where that experiment is very important, is controlling those variables. And you'll see these little mice in the corner, and where experiment is the test. The truth is the science.